Okay, accelerating data analytics with computational storage drives with my esteemed colleagues. Happy to be here with the diehards on FTI day here. So first, let's talk about what is a computational storage drive. Well, it's basically an enterprise SSD with all the bells and whistles and performance you'd expect from something you'd plug into a server. And we're going to add compute offload engines, and those are things that act on data as it comes into the drive, as it leaves the drive, or can act on data within the drive without a lot of host orchestration. So we call that a CSD, or a computational storage drive. And these offload engines, they could be fixed RTL and a controller. They could be programs you run in an embedded ARM CPU, for example. They could be FPGA. There's not a constraint on what comprises an offload engine here. But the key point is that it exists on this CSD itself. So why would we bother doing that? Why use a CSD? Well, as we go to Gen 4, Gen 5 PCIe SSDs, the bandwidth afforded to the host is just extreme. And so we run into memory bottlenecks. And even if we don't have a memory bottleneck, you have to have the CPU to go process that data. So what good is shoveling tens and tens of gigabytes per second to the CPU if the CPU can't keep up? So the fundamental concept is let's push some of that compute into a CSD and help out the CPU that way. So we alleviate some of those memory bottlenecks. We're going to take a load off the CPU. And what's nice about this architecture also is that it scales with the amount of drives I add. So I add another drive. I add a little bit of complementary compute to my system. So we say in kind of marketing speak, we go from a CPU-driven architecture to a data-driven architecture here. So changing gears, let's talk about data movement. So typical disaggregated infrastructure, you have a bunch of compute nodes, things that look at things that want to access storage across a fabric and a storage node. And so it doesn't take much to see that where one of my possible bottlenecks here is moving data from my storage node across a fabric into my compute nodes. And if we look at that in the context of analytics, right? So analytics, what does that mean? That means that I have a database, column store database. I want to, let's say, do a scan operation. I want to go look at my data in a storage node, but I look at it in the compute node, right? So I've got to bring all of that column store data across my fabric into my compute node. Well, it's an old problem, right? And so they say, well, what about scan pushdown? That's my solution, right? Well, yeah, sure. You can push scan down into your storage node, but then you're right back to where you started, right? Now you've got all these SSDs in the storage node, and they're going to overwhelm your CPU. They're going to overwhelm your memory. And you're going to get bottleneck there. So you either got to throw a lot of hardware at it and make your storage node really expensive, or we could do a CSD. And we can do some scan processing within each of those CSDs themselves, right? And so very straightforward to imagine if I can cut down on the amount of data that the SSD itself is sending to the CPU, I'm reducing that data movement. I don't have to move so much into memory. And I'm removing my processor burden. I don't have to ask the CPU to look through data that can't possibly have what it's looking for. Of course, it's not, it's too good to be true, right? There's no free lunch. So, you really need flexibility to support different column store formats, right? It's not something you can just put in RTL and run really fast and call it a day. So that implies that these scan engines really have to be programmable, which means you have to run them in an embedded core on this SSD. And that really gets you to a point where maybe you have inadequate scan performance. And why is that? Nothing competes with a host CPU. I mean, the power, the performance, everything is the best general purpose processing that you're ever going to get. What we have in a CSD is going to be typically in a controller that's maybe limited to under 10 watts. It's going to run at a slower frequency. It's just not going to have the kind of oomph that an x86, for example, would have. So what do we do? Right? Give up, go home? I don't know. What we really need to do is prevent these embedded cores from really becoming the bottleneck, right? And the only way to do that is make it a way so they don't have to look at everything. So if I don't have to look at everything, I can cut down on the work I have to do within those embedded cores. And so what we're going to do is we're going to take that column style format. So normally we just shove the data in there in a column store file. But what we're going to do is we're going to add some metadata to that. And what that metadata is going to do is going to allow the embedded core to decide whether it needs to process that data or it can just skip it and move on. Oh my gosh, how does this work? So what we're going to do is we're going to look at column data. And let's use human scale numbers. Let's say our column range is from 1 to 100. Obviously, not real world, but works for my little brain. Let's take that column data where we have a range from 1 to 100 being the maximum value of my column store, 1 being the minimum. And let's do something simple. Let's chunk that into 10 buckets. So a value of 1 to 10, 10 to 20, 20 to 30, and so on. So I've looked at my data, and I can drop the data into one of these 10 buckets. So what I'm going to do is I'm going to take, instead of just storing my column store data by itself, I'm going to chop it up into little chunks called segments. And in each of those segments, I'm going to look at all the values in that segment. And if I see a value that falls in one of those buckets, I'm going to set a bit and a bit mask to 1. We call it a segment skip mask. So let's say I have a 9 in my first segment, and I have a bucket 1 to 10. I'm going to put a 1 there, say, yep, I have data that fits that criteria. If it doesn't have, let's say, value 11 anywhere in that segment, that second bit that's from 10 to 20, set it to 0, nope, that data can't possibly be in this segment. So now what I've done is I've created these segment skip masks that I'm going to store alongside the column store data. So now when I go to do a scan operation, when I look at all this data, let's say I'm looking for that value 9. The ARM CPU, all it has to do is pick up the segment skip mask first before it touches the data, look at that skip mask and say, is there a bit set for 0 to 10 or 1 to 10? Yes, 9's in here. OK, great. I need to process this. Okay? And if it was 0, for example, let's say the value I was looking for was 11, it would just drop it and move on. So nothing happens. Nothing gets transferred to the host. Nothing gets processed within the ARM. But let's say it is of interest, right? I have that bit set. My mask matches. Now I've got a decision to make. Do I want to pass it to the host, or do I want to process it inside the CSD? Actually, the first thing I want to do is send it to the host, so I can get my CSD just moving on to the next segment and get that queued up, right? But if the host starts getting overwhelmed, and remember we had that problem we're talking about where we don't want the CPU just to be saturated, then we can push that back down onto the CSD, and the CSD can start helping out with some of that scan processing. So the decision really comes down to how saturated is my CPU. If it's really busy, then I'll start offloading that onto the CSD. But no matter what, I am limiting the amount of data that I'm sending up to the host. So what this really is a software hardware co-design kind of approach, right? Where I'm setting a set of trade-offs. I have to do a little more processing to prepare that column store data. I'm taking up maybe a little bit of extra space to save those segment skip masks, but I'm going to get a big payoff. And what's that payoff going to be? So this is the benchmark that we ran. And this is using 8 Cortex A-53s. So those are pretty mainstream, embedded ARM. OK, just remember the bars go up and to the right. OK, and then it'll all be understood. Up and to the right, like all good slides. Anyway, so what we did is we take TPC query 6, the line item table, and what we're going to do is we're going to say, OK, let's see how much we need to chop this up to get, and what kind of benefit we get with different segment sizes, right? So obviously, if we look at the original, that's our baseline. And if we only use like 1,000 numbers per segment skip mask, we don't get that much improvement. It's actually not so great. Now we go down to 128. Now we're starting to see some benefits, right? We're halving the latency by adding having that 128 value granularity. Actually, it turns out that we saturate around 32 values with the skip mask there. And it's kind of intuitive why that is, right? So the bigger my segment, the more chance I have that I match. The more chance I have to match, more I have to go do and look through and I have to figure out whether my value actually is in there or not. So the idea is that the more fine grain I can get, the better my performance can be up to some point where I saturate somewhere else. So it was a pretty cool kind of proof of concept. And this isn't really a product per se. This is just an idea of some of the things we can start thinking about when we have heterogeneous environments where we have these compute resources in our SSDs. And hopefully it inspires some future work and future ideas that can actually be realized in a real system. So with that, I think I'm well over time with my technical difficulties, but thank you.